Shall we begin? My name is Paul Wright. I'm honored to be the CITRIS Director, and I'd also like to welcome our web viewers at the other three campuses of Davis, Merced, and Santa Cruz. These are our Wednesday talks, and as you know, on Fridays we have our talks focused on energy. And this week, since it's our first one, you always want to start with the very, very best and end with the very, very best. So having Dr. Laura Haas from IBM, who's a National Academy member. She's been at the IBM Academy of Technology. She's an ACM fellow, and she's vice chair of the board of the Computing Research Association. She's a national figure in this field of information to foresight. She currently is director of IBM's research institute related to massive data, analytics, and modeling. It sounds like the King Kong project. And she recently was the director of computer science at IBM's Almaden Research Center from a long period of 2005 to 2011. She's best known for her work on a query processor called Starburst, a system called Garlic, which is a system for the integration of heterogeneous data sources and for warding away evil spirits, and on something called Clio, the first semi-automatic tool for heterogeneous schema mapping. It's a great pleasure for me to look around the building here and see so many of my distinguished colleagues from computer science. In fact, there's so many of them I shouldn't call them out because I'll miss them. Then also I wanted to specifically thank Dr. Masoud Nikravesh and Dr. Hugh Aldridge, who have been working with Laura on some of the important programs in water and especially on getting beyond the bits. So let's join with a warm welcome of applause for Laura Haas.
Thank you so much. That's very sweet. Okay, is this on? Can you hear me? Good. So what I'm going to do today is try to tell you about a little bit about the less glamorous side, if you will, of doing analytics. Everywhere you go, people are talking about big data and getting value out of data and doing analytics on data. And mostly what I want to do today is talk about what it takes to get from the raw data to a place where you can actually start to get this kind of insight, where the domain scientists, if you will, can actually drill into the data and understand what's going on and start to see things of value. So it's sort of the dirty secret of big data. It's the underpinnings of what goes on. I'm going to try and make you believe that it's actually remarkably interesting. So that's my goal for today. So just to set the stage, oh my, that's the problem with using your own little thing. Okay, well, we'll figure it out. It's clipping the top, so in terms of stage setting, I don't think I really have to dwell on this. We all know that there is a ton of information out there, more and more data online every year, ranging from very traditional databases, which are up in the hundreds of the hundreds of terabytes sort of areas, to very untraditional sources of information, such as all the data on the World Wide Web are coming in from mobile phones and so on. The cool thing about all this different set of information, this is sort of a problem. I'm going to see if I can change my resolution and help. Please excuse me for a second. Desktop.
Just bear with us for a second.
Yeah, I'm sorry. It's just clipping way too much of it. Yeah, properties. I think, yeah, settings. Right. Yeah, 1024. There we go. Let's try that. And, all right, let's see. He swears this will work. We'll see. Okay, let's try this. That's better. Yes. Okay, sorry. That was a little too clipped for me. Okay, so the wonderful thing about having all these sources of information is you can start to do some really important and cool things with them. Whether it's sort of traditional business, this thing we call multi-channel customer sentiment. That means letting your favorite store know really all the interactions you've had with them, whether you walked into their physical store and bought something, or later called them to complain, or wrote complaints on the web somewhere, or maybe praise on the web somewhere. Doesn't have to be all bad news. No matter how you are getting access and touching this company, they want to know the whole history of your interaction so that they can serve you better, right? Very traditional business. Maybe a lot more heartwarming are things like work we're able to do now in hospitals, whereby putting the right kinds of sensors in, for example, a neonatal environment, we have been able to show that you can help doctors detect diseases, infections forming in these very, very premature babies 24 hours or sometimes even more ahead of when the full symptoms break. And of course, the earlier you can detect problems, the better chance you have of curing them and of saving lives. So there are lots and lots of different examples where bringing together varied types of information can actually help people do things that are of value. But it's not really an easy thing to do today. Today, it takes a huge amount of effort to get there. And if you look, in fact, at the inside of any of the sort of groups, the corporations or whatever, who are trying to build these applications that bring data together, you see a rare mess. You see that they have their online transaction processing systems, very structured data that they've known how to deal with for years. They typically have web sort of data and others where they're getting to see what clients and others are doing. So kind of data with some structure, but coming very quickly and coming often in bursts, and so it's partially structured. They have feeds coming off of web data that they have to deal with. They may be reaching out to social media, and they've got incredible volumes of data. So if you're trying to think about what do I have to do to put together a new application that's going to use data from multiple of these various sources, you find yourself very challenged. And in particular, there's typically a huge process that people go through before they ever even start to talk about doing the analysis and doing the analytics. That would include things like just acquiring the data, just getting the data and getting it into systems where it could be analyzed. Figuring out when data comes from multiple sources, how to align it so that you can see what are the objects it describes and understand everything about that data. Then there's often a lot of transformation that's needed to get the data into a form where you can ask the kinds of questions that you want to ask on it. And after that, lots of analytics that want to be run, but how do you build those analytics applications? How do you put them together and understand what's going on? Finally, to a place where you can really start to look at the results of your analysis and understand it. So what I'm going to try and do today is take you through various parts of this process. I won't take you step by step. I'm going to show you little bits of some of the projects and work that's going on in my laboratory in terms of addressing this whole cycle of things that we're doing. So let's start with just acquiring data, especially unstructured data. If data is already nicely in a relational database, it's not really very hard to get it into an analytics system. But a lot of the data that I mentioned, that we've been talking about, comes from very, very diverse kinds of sources with a lot of unstructured data, images, text, and so on that you have to deal with. So we have a project we call Mongoose. Don't ask me why. I don't know. We like funny names. They have particularly been looking at healthcare information, but in fact, they have a general sort of flow control pipeline architecture to help acquire data. And you can see as data comes in, you have to first get the data in. Because it's health, you want to get the personal health information out. Then, depending on the subtypes of data, you may want to go through a bunch of different pipelines and then be able to publish your now acquired result into a store from which you can do more analytics. So the types of pipelines you might get, if you were, for example, a cardiology application, you might be looking at an echo video, an EKG, some unstructured text from the doctor's notes, and then some structured data from lab results, all of which has to come in and be munged. But I'm just going to focus for just a minute on that little box data ingest, which you think, how easy. I just put a wire from this database to in and into my system, and everything should be fine. But just to deal with that turns out to be not so easy. You get a range of things that can go wrong, and that it's very hard to describe the reactions that you may be able to do with this. So even at the very beginning of getting data in, there's sort of multi-stages just to get the data in the door and to deal with all the issues that are in there. More fun, though, up ahead. So now you've got data from various sources perhaps coming in. In this case, a simple example, we have access to some Twitter data and Twitter feeds, and we want to learn everything we can about the people who are tweeting. I won't say twitting. So in this field, from these feeds, you can find out a lot, and there's been a lot of progress in information retrieval and text analytics and so on that's allowed us to do some pretty cool things. Some of it's easy. The metadata on a Twitter account will tell you quite a bit. You can find out the name of the person. You can find out their screen name, right? You might be able to figure out from what they post about themselves that, in fact, there's a location, that this is a woman, says it's a gal, and that they're in Tampa, so they're in Tampa, Florida. Then messages start coming, and you can learn a lot more if you can correlate them, of course, to the individuals. And that's a pretty easy correlation because we have a screen name that links things together. So I can learn that this woman has a son, so she's a parent. Somewhere in here it says, thanks for coming in last night, looking forward to yoga. Okay, so she must do yoga, and so on. So you can learn a lot. And that's relatively simple with today's technology. Then things get more interesting, though. Suppose you take another source of unstructured information, in this case BoardReader, that goes out and reads all the blogs around. There's a person who's posting there named Champagne Girl. No valid name, no metadata, no location. And she's got lots of posts about food, so somebody obviously interested in food. We can link the posts together because we know we have a single ID. And in one of those posts, once upon a time, she says, be sure to follow me on Twitter at Tracy Gita. Can you put those together to flesh out a broader profile of her and start to understand who her relationships are, more about the kinds of food she likes, and so on and so forth? It starts to get a little spooky and scary, right? But the technology is there today to do this, folks, okay? So students in the room, be careful what you post. Okay, we're watching. No, IBM is not, actually. We're just playing with canned old data just to see what we can do. But there are people out there who are watching. So watch out. That's been a public service message. Okay, so this is kind of cool. And once you've kind of built a picture of what are the entities here, the person, right, that's of interest here, the poster. You might also be looking for information on other entities, such as maybe what you're really doing is trying to find out all the people who like Bubba's Buffalo Chicken Dip or whatever, I don't know, but Bubba's Buffalo Chicken Dip could be an entity that you would care about to group information around. Then typically you need to take that data that you've extracted and you need to transform it in some way to get it into a form you want. Now this is the first area that was ever really worked on back in the early days of information integration, the first times that we started to have multiple sources of data. And so there's some very old and tried and true technology here for doing these transformations. And there's two major techniques for doing that. There are what are known now as data warehouses and data warehouse tools. We think of this as eager integration in the field. So we would talk about this by a whole bunch of different names, but I'll call it eager integration. Why is it eager? So the way these tools work is they take data from multiple data sources. Here I'm showing databases, and the colored columns are the ones we're going to select out. So we take part of the information from multiple sources. We run it through some sort of processing that transforms that data, munges it, and puts it together in a particular new form, usually in another database. And we do that ahead of time before anybody asks a query on it. We prepare it once, we get it ready, and then when people want to ask queries about it, it runs like the wind. They get an integrated schema to ask, and they can ask lots of questions, and they can keep asking about this, but this data is now in a beautiful format that makes it very easy to work on. So the problem with this is, of course, if you didn't know what you were doing, you might have gone to a lot of work to gather this data together and then never access it or reference it. Or you might find out 2 weeks after you did this that, in fact, you really did not get all the data that you needed. And that wouldn't matter if it was, an hour to turn these sorts of things around. But the traditional engines and these traditional big projects, they spend a lot of time going through job after job to kind of get the data together and into this polished form. There are a lot of stories of sort of your typical warehouse taking about 6 months to get up and running. But there are a lot of really bad stories of warehouses that took 2 to 3 years to get off the ground, and then they didn't necessarily meet the needs of the project. By then, the world moves on. It moves pretty fast. In 3 years, probably what you're going to need is not what you needed when you started. So because of those sorts of issues, in the early 90s, we started working as a field on a different kind of technology, what I will refer to now as, in contrast, we had eager integration, we have lazy integration, and this one is kind of at the opposite extreme. In this case, you don't move any data until somebody asks you a query. And when they ask you a query, what you do is you go out and in real time divide up the query, send it out to the pieces of data, wherever they may be in their separate sources, bring them back together and put it together. So this is wonderfully flexible. People have been able to get things working literally in days and get a sort of stable installation in a few weeks that has all the bells and features they want. So much more easy to kind of go through and transform your data using this sort of approach. But of course, because it wasn't prepackaged in advance, because people may be exploring with the queries and the system isn't tuned for those queries, performance can sometimes be a real problem. So it's at the other end of the spectrum. Both of these are, however, pretty well understood technologies. They kind of got hardened in the around 2000 or so, and they've grown and they've gotten faster and more efficient. They can reach more types of data sources. They've grown in a number of different ways, but we still kind of have two extremes of the spectrum. Each has tried to add a little bit of the other, but one of the really hard problems as you start to bring data together, if you're one of these people who wants to do analysis, is figuring out where do I want to be in this space. So if you're looking for interesting research questions, people would die for one engine that could kind of span that and that would choose the right point in that spectrum from lazy to eager that would automatically conform to a sort of description of what it is that you are wanting to do. So if you could give it your requirements in some non-procedural sort of form and then compile into the right place in the spectrum, this would be a really cool thing to be able to do. Okay, so now we have acquired our data, we've figured out what the entities are, we've got some way of putting it together. What's left to do? Well, first of all, as I said, this is well understood technology, but in fact, new data types have kind of forced us to rethink some of these pieces. And one of the things that those other systems were sort of tailored for was structured data. As we've tried to deal with more text and unstructured data, we've had to look at very different types of pipelines. So this is a project at Almaden where we are looking at how to, in essence, bring warehousing to unstructured data. Unstructured data is a very extreme case of data not being in a form that you can easily analyze. How can you do something interesting so that you can take text from over here and transform it into some model where you actually have some understanding not only of what's in this text, but of the relationships between the different things. So this is an example, and this is where this is called Midas because touch of gold. We took SEC data, so from the Security Exchange Commission, public data out there, lots and lots of forms. Every public company has to file a ton of forms when all sorts of things happen in the course of their year. They also have their tax returns, et cetera. Other information from the Federal Depository Insurance Commission, FDIC. Beautiful documents. If you could somehow have a picture in your head of what those documents are telling you, you could find out lots of things. For example, suppose I am a bank and I lend Tim here, I was falling asleep in the front, some money. And, you know, I loan a lot of you money because that's what banks do. But some of you are banks. And Tim's a bank, and he's not very careful, and he goes and lends money to Mike, who's falling asleep in the back, but never mind. Over time, a lot of my money could have drifted through a lot of you to Mike. And if Mike turns out to be not investing too wisely, and he goes belly up, we have a mess. Right? We had a very big mess in 2008. This wasn't the only cause, but it was part of the cause. And part of the problem is it's very hard for banks to know where their money goes after it leaves their hands. They know where they loaned it to. They don't know what the people who got it necessarily did with it. But that information is all in the SEC and the FDIC forms. You can actually get all of that there. And so what Midas is allowing us to do, going through this sort of a pipeline of jobs, is to extract from this unstructured data where information is spread across many, many kinds of documents, that kind of structured representation, which then allows you to do very simple analytics and start to see what is my exposure, where has my money gone, and how reliant am I on the fiscal health of this sort of source. So this is an example of using text plus the integration and transformation sorts of ideas, plus, of course, new results on how to find the entities in the text to start to do some very powerful analytics. Of course, speed is always an issue. We're dealing in an age where petabytes are starting to sound small. Every other day there's something on zettabytes or yottabytes or whatever, and I don't even know how many zeros there are in those. It doesn't really matter. What everybody is saying we need to do is highly distributed systems, do a lot of processing in parallel, and optimize that. And so we are, of course, working on one of these systems. We have a Hadoop box in the middle. This is an open source system that allows people to very easily distribute work and then collect it back together to process it. It's a very, very simple programming model for it. But we have focused on doing some extensions sort of above, underneath, and around, as it says Hadoop. Sorry. Some of the things I'll point out here that I think are kind of really cool. I've actually been talking to you about System T all along. It's System T for text. They want to be for text what System R was for database, for any database students in the room. That is the technology that we're using to very, very rapidly scan large volumes of text and pull out concepts that will allow us to do applications like that Twitter one, like the Midas application. So it's kind of underpinnings. And the goal of this kind of a project is to make it much easier for people to pull information together and then to write more advanced analytics on it. More recently, we've started looking at machine learning and the very many different kinds of machine learning algorithms that people want to be able to write, the problems that are addressable by having the machine start to learn there, and focusing again on a way of creating a higher level of abstraction for the folks writing the analytics that will let them more easily express what they're doing, and then under the covers will optimize, will actually write what needs to be done and deal with the very distributed nature of the data and the processing that's going on. So in all of these cases through here, what we're really looking for is, instead of letting you use this dead simple, but you got to control it yourself programming model to scale out your work, can we make it easier for big classes of problems to express what it is that they need to do? And we've been applying this in systems like Midas for finance, a system that is in the consumer goods area, retail area, if you will, that helps companies understand what people are saying about them on the internet so that they can get a better sense of how their brand is being perceived. We've been working with healthcare pipelines, looking at how do we do a similar thing where we can give you an easy way to program pipelines for image recognition, for example, so that you can, I should not say image recognition. We know it's a picture of a heart. It's image analysis, so you know what's going wrong with the heart. But so that those again can be without the expert in image recognition having to think about how do I program this big distributed system, make it really easy for them to express what they're trying to do, and then have it automatically parallelized and working properly for them. Okay, so a system like that one, which is now a product from IBM called Big Insights, this whole big stack of stuff, is really useful for doing analysis on huge amounts of data. But that's only a piece of the problem that we have with data today. So this chart is kind of a useful one. It talks on the bottom here on the x-axis about how frequently am I going to make decisions. Do I have to do it, once every few months, or do I have to do it in microseconds? And on the y-axis, it talks about how much data am I making these decisions on, starting from kilobytes, which when I started in this field, megabytes were large databases. It's very scary now, but at any rate, going up into the exa and beyond. And what you see is that a system like our traditional data warehouses tends to fall in this area where they deal with terabytes, maybe, as we said at the beginning, hundreds of terabytes getting up there. They have to return answers or results within minutes to seconds, but if it's a really complicated enough query on enough data, people sometimes will be willing to wait for hours. So they're in this space here. As we start to get into new territory, this is where things like that Hadoop system come in, where you're doing deep analytics on vast amounts of data you can do it pretty fast because it's highly parallel systems, but you're typically not trying to respond in microseconds. There is a whole nother class of problems. For example, the one I talked about with the baby at the beginning in the neonatal ward and the sensors which are streaming data out at the system, where in fact you want to react fairly quickly, within minutes to certainly to even faster if you're using a control system that's actually going to like adjust the amount of oxygen flowing and so on and so forth, right? And for that, there's a new class of systems emerging, or not so new anymore. There's a new class of systems emerging in the commercial world around streams. We have some work on that. But there's this whole area in the middle that's becoming increasingly interesting to people in terms of analytics, and a good area, I think, for research in analytics infrastructure. How do we make the linkage between these kinds of systems, the ones that are very good at very fast data coming at you, but not huge volumes typically, because they usually want to make a decision based on some very carefully digested stuff, a small amount of that, and some very current new signals. How do I make a linkage between that sort of system and one of these that can build, that can churn for however long it needs to over large amounts of data to do that? Why would I want to do that? Well, if I'm AT&T, for example, or any of the phone companies, and I have models that I do of my consumer population, right? I know who my clients are. I have them kind of lumped into big categories. I have these big models that I run over all the data of all the transactions you've ever done, all the places you go, how you use your phone, et cetera. And I know you, but at some very gross level. Increasingly, they're starting to know you at a very fine level, right? So what these big, deep processing systems have let them do is it lets them start to make very, very small, fine-grained clusters and kind of know who's like who on a much smaller group. So where before there might have been 10,000 clients in a group, now there might be 100 or even smaller. Huge amounts of processing, not something you really want to do in real time, but on the other hand, they really do want to react in real time when you are standing outside a store in the mall and they kind of know, if they offer you a coupon for this, you'll go in and you'll do something at that store, right? They'd like to do that because the stores would reimburse them for directing clients their way and so on. But what if it's not a store you're usually at? They want to kind of find in real time all the comparison sets that are kind of like you. And so again, there's lots of data, there's lots of different clusters and groups, and they're getting real-time information about your most recent behavior that they're trying to use or want to be able to use. I don't think they can actually quite do it today, not on the fine-grained level they'd like, but that they'd like to be able to use to help you do whatever it was you were about to do better, to predict your behavior in a better way. So streams, lots of different systems, good one from Berkeley. The idea here is just that streaming systems make it easy to take very different kinds of data, put together little pieces of smart function, link them up in a way, and pull them together to make a much bigger whole where you can bring in all sorts of different information to that. Now, stream systems today typically either are kind of tied to a very databasey model or are typically much more sort of flow model driven, where you program these things independently and have to hook them up. And that's been one of the problems. Something like this is very flexible, but can be a little bit harder to program than something that uses a higher level language. Higher level languages, though, tend to be a little more restrictive in their programming model. So another place where work is going on to bridge these. So I've talked a lot about how you get the data in, how you can process and transform the data. Obviously, you're doing this for a purpose. You're going to do various kinds of analytics on this data. If you think back over what I've been talking about, you'll notice that actually analytics has been happening all along here. Analytics happens at pretty much every stage of the process. But people are using, charts like this to talk about all the different kinds of analytics that people want to do, ranging from fairly simple analytics that we used to be able to do back in the good old days with the first arrival of databases, descriptive analytics, as that's often called, up into to very complex, mathematically challenging sorts of optimizations and so on that can go beyond predicting the future to actually making the future happen for you. With all those different kinds of models, there's usually a little bit of a challenge in figuring out how to create the next kind of analysis you want to do. And we see this very clearly in complex domains where typically the system that you're trying to describe and analyze is so complicated that not one model can kind of span all of that. An example of that kind of system is a healthcare system. Just to take a very simple example, if you are looking at how to reduce the incidence of type 2 diabetes or obesity and so on in the country, you find, on one level it's very simple. Everybody knows if you want to lose weight, you reduce the number of calories and you increase the amount that you eat and you increase the amount of calories that you burn. It's a very simple equation. But what goes into reducing the amount of calories that you eat? Not so simple. It turns out it has a lot to do with how close you are to a really good quality supermarket. There are inner cities, including Oakland, where you can have to go literally miles to get to a place where you can get healthy food. So that's gonna have an impact. Similarly, on the output side, if you're in a place where it's relatively easy to get to exercise, it's places where you can exercise, whether it's a gym or the streets to go walking or the hills and so on, great. But again, distance will play a factor. Well, distance is interesting because what does distance matter if we have really good public transit, right? It becomes easier in some places than in others. Typically, it's very hard to build a model that takes all these different things into account. And so one of the areas that we have been working on is enough with data integration. What about model integration? When is it mathematically reasonable to start to put models together? When is it, how do you enable that? How do you describe models so that people know what it does, so they know whether it makes sense to take one model and put it with another one? These are the sort of problems that we're now starting to look at in this project called SPLASH at our lab. So I mentioned before that with streams, or any of these tools that kind of do data flow diagrams. Data goes in here and gets processed and goes to here and gets processed. It's a natural way to think about things, not always as easy as you might think, though, to work them out. And so another way to kind of mash up these different pieces of analytics is using something like an inquiry compiler where somebody asks their query, determines the result, and the system actually figures out which things to put together in order to deliver the result. And so that's another area where there's, I think, a lot of interesting research questions. It can build off of a lot of the work we've done on standard compilers in the past. So you've got all this stuff together. I can't leave a talk on analytics without mentioning visualization, right? People want to be able to see the results. One of the trends here, and we now have some startups that have come along since we started the Many Eyes project a while ago, but one of the trends is how do we collaborate around data? And then the other sort of dimension to that is, how do we go from more standard data that scientific visualization, and we've had pie charts and bar graphs and so on for sort of normal structured data, how do we start to visualize information about text? So this project, Many Bills, is an attempt to help people understand the bills that are going through Congress. So it's using text analytics under the covers. It's using very clever visualization to help you see where all these little strange things. You know how when a bill is passed in Congress, you often find that it had some unanticipated consequences. This is how these new ideas come in, because Congressperson A makes a deal with Congressperson B and tries to kind of tie tie their success, the thing they want for their constituency, to some other totally different bill. Anyway, I recommend going out there and looking. It can change your view of the U.S. system of government quite substantially. Other things, not necessarily for the better. But other sorts of things in the visualization collaboration space that come into making analysis work are helping people understand what analyses to do and how to think about analytics. And so we have some projects that are really trying to help you understand how to make decisions of various kinds. At the moment, they're working on relatively simple consumer decisions, but the idea is to start to see how you could guide people through a complicated analytics process, again, helping them understand the goals and the tools available to them. So my latest role in the research pantheon right now is, as Paul said, is around something we're calling the Institute for Massive Data Analytics and Modeling. There's a very clever acronym in there that I'll let you chew on in the background. But the idea of this institute is kind of put together a lot of tools like this one and bring them together with people who really want to do analytics, who have large amounts of data, who have expertise in what to do with that data, but really don't want to deal with this kind of dirty underpinnings that I've been talking about of bringing it together. The Institute, heaven willing, as I get it up and running, will involve, of course, IBM Research, also our commercial partners to kind of bring in problems, and government agencies and academicians to work with us. In fact, we have been working with some of our colleagues here in civil engineering and environmental science and so on around water management, and very interested in doing something in this space. So again, the idea is to take really hard challenges that you couldn't, no one group maybe could solve all by themselves, no isolated researcher is going to hit on, and then help our research by getting both problems and data issues and having to help users make sense out of it, but also help the researchers' interest, the researchers' research by allowing them to just kind of have the benefits of this kind of powerful stack of infrastructure to help them, and researchers who can help them leverage and use that stack and who are trying to improve that and make it easier for them. So that's kind of what I'm up to. I will end there. Just sort of say what I've tried to show you very quickly today is that there are a lot of advantages to collecting more data, but you have to do a lot more than collect it. You have to really today understand the uses and plan for them. It's hard to do that. Today you need to be a rocket scientist almost, or at least a data scientist, a term that's gathering a lot of currency here, to understand how to work with this data and get it there. I think a very fascinating area of research for us all is how to bring these technologies to a point where it becomes easier and easier for people who understand domains to actually work with the kind of data they need to to solve problems in them. Okay.
So we have a few minutes. I'll share. We have a few minutes for questions. So. Questions?
Hi. You mentioned many interesting and cool applications in this talk, and very interesting. But my question is, so you also mentioned like framework platform, but I didn't see, like, is there any generic platform you can apply to these applications? Or I see many ad hoc methods to each application, so.
No, so the picture I showed around Hadoop, we actually have a fairly generic platform there with a lot of fairly powerful tools in that. So but you're correct in the sense that we still don't know all the tools that we need, right? We have a tool that makes it much easier to do text analytics because there's a ton of that going on. We know that people want to do a lot of machine learning, so we're adding that. We will continue to build out tools in that platform until we, as we learn kind of what else people want to do. There's been a lot of work, for example, on integrating R and statistical methods into that platform. So that's a fairly powerful, fairly generic framework, but it still, frankly, takes too much intelligence to know how to use it best. Right.
There's another question here.
Uh-oh. I see.
At the very beginning of your talk, you made a comment about scrubbing medical data, and then you showed a whole bunch of examples in which identity is key. If I had some notion of what I mean by privacy, how do you model that in systems that are getting this complex, and how do you figure out where to insert filters or whatever technology?
Yeah, so that's a wonderful, wonderful question, and it's a huge area for research. What we're doing today, practically speaking, is the filters go very close to the data itself, and they're very type specific. So the medical guys, they know what the HIPAA laws are. They know how they have to do this. They will pre-process certain types of data at the earliest point they can in a pipeline. They can't often do it until they know that the different parts of a record are complete. So you've got to kind of get a record together, pull all the information out that identifies the patient in there. That turns out to be a really hard task because doctors say things in notes that your standard system won't know is identifying information and so on. Other areas are obviously somewhat less sensitive in the sense that people volunteered the information. They may not have realized they were volunteering it. One of our big problems is why I use that example. But even then, I think the challenge and the furor around Facebook and its constantly evolving things is people really don't understand what you can do out there. And there are a lot of systems out there right now that are pulling information from Facebook and LinkedIn and blah, 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 and pulling together a portrait of you that you may not be very happy about if you go online and start to look. So this is an area that's really ripe for some better solutions for us as individuals as we go out there. We have in IBM, we have a whole set of lawyers making sure we don't do anything wrong, right? And I think a lot of the big companies do. The younger companies, they don't care, right? They don't have deep pockets to go to. So it's not pretty.
Could you comment on what you think the role of artificial intelligence is on data integration? And one thing I'm thinking of is the Watson system, where it integrated all that data to answer the questions in Jeopardy.
Yeah, I love the Watson questions. Oh gosh, if I never given I love Watson actually. Don't get me wrong. But it is true. If your name is IBM, if you have IBM in your letters right now, you can't give a talk and not talk about Watson. So I think there's actually a ton that AI, or in its more popular phase right now, machine learning, has to say about doing this. And if I were a young thing and starting over, that's probably where I would go and try and apply things, because this is a classic, very hard problem that takes a lot of people, insight, depth, etc., often sort of flashes of inspiration to get things from. And I think we might well be able to apply this. So that for the first half of your question. Watson, so Watson, I can't give you a whole Watson lecture in 2 minutes, but Watson is actually downstream from everything I talked about today. And in essence, it's a machine learning application on top of a lot of text processing and so on. And so it's doing, it kind of works in phases. There's this huge offline phase that basically uses the infrastructure I talked about here to go out and go through tons of text and digest it and pull out things that it thinks are interesting and so on, and largely index it, right? And so on. And then when a clue or a question comes in, it's doing first a search, just a blanket search to develop candidates, and then based on things it's pre-learned and based on new learning it does in the course of the games, it is going out and doing focus search to get evidence and figuring out how to combine that evidence. And there's like 1,000 different machine learning little algorithms in there for little pieces of that. But you can think of Watson, to all intents and purposes, as something upstream from this. Doesn't mean that you shouldn't take some of those machine learning things and try and do that earlier downstream. Could help.
Thank you.
That's just because I said he was sleeping.
The red light's on. It's supposed to be on.
Oh, okay. So you've got a pretty ambitious agenda of taking data from all over the place and integrating it, taking models, which are scary enough, and then integrating those, probably having to fuzz the data and do other things to it to preserve privacy, and then building it, kind of piping it through this huge software stack. And I guess my question is, how do people using the system know whether they can trust the answers that are coming out?
Yeah, that's another really, great area of work. Today, that there's a lot, before we start doing things on massive amounts of data, we actually, like everybody else, do sort of can process. You run a small amount of data that you're pretty much sure you know the answers for through until you get confidence that it's doing the right thing with them. And then you let it loose on the world, right? Is there a better way to do that in future? It would be nice, right? Maybe there are places where machine learning can help, or where Watson-style reference to expertise. We're asking people today, is this right? Maybe there's ways to use that sort of Watson capability to do that. In fact, our mathematicians in Watson are actually trying to do that. Use Watson to solve one of the basic problems in machine learning, which is how do I get my set to learn from in the first place? Well, today we have people mark what's right and what's wrong. Can you use Watson to kind of prime that loop? Watson, loosely speaking, same sort of thing. So that I think is one of the more clever things that they've thought of to do with Watson technology. So.
Thank you, Laura. One more.
These people are diehards.
One day I will fall down the stairs.
So many of the kinds of analytics that you describe are not at the stage where they can offer completely correct, 100% guaranteed answers. For example, extraction from text, face recognition, name resolution, and so on. And in that case, a unidirectional pipeline fails, because when you do uncertain reasoning, that's the first thing you learn is that unidirectional is not correct. And it seems like every system you described is predicated on a unidirectional pipeline.
Yes.
So what do you do?
The state of the art today, I've written a paper on this saying that we have to fix that, but I haven't fixed it, so I can't take any credit. The state of the art today is you realize you did something wrong, you go back and try and do first the last phase of then you try and figure out where did you go wrong, and you run it forward again, right? And so that's very, very annoying. I mean, there's just no other way. That's why warehousing systems, sometimes warehousing things take 3 years, right? Because that's something where you don't get any feedback for a long time about what you've done, and then figuring out whether the data was wrong or down near the source, or whether you did some complex step in this processing was wrong. It becomes very difficult. People are working on debugging aids, so that but it's still predicated more or less on a one-way flow. That is, stuff goes in, something went wrong. Now maybe I have some tools that help me see what happened to the data at different points. Maybe I can take examples and trace them through this complicated transformation or analysis process. Our System T text system has lovely tools now that will let you see the impact of any rules that it's running and so on, so you can kind of tell it, this is wrong, and have it show you why it was wrong, and things like that. But it's still basically one way, correct it and start over, right? So another great area for research is to be able to make those directions go a little better both ways.
Thank you, Laura.
Okay.
Unless there's one more quick one, we'll call it a day and let Laura have us some lunch.
Oh,
She's
thank you.
sitting here.
Thank you.